Hello students, we are going to start capacitors, its concept, its understanding and questions based on capacitors. What is capacitor? First the question arises, what is capacitor? It is a very common useful device, electrical device that you will find everywhere in your house. In fan you will observe that there is a capacitor. In common language, in the language of mechanics, the capacitor is also called as condenser. So if you have got the chance to see the motherboard of your computer, then you will find very small, many different cylindrical structures. Those are basically capacitor. So capacitor is a device that is being used in our day-to-day life. Everywhere, almost everywhere we use this capacitor. In motor also there is a capacitor, in fan also there is a capacitor, and many places the capacitor is used. So capacitor is widely used electrical device. Now what is the capacitor? Capacitor is a device that stores electrical energy in the form of electric field. It is a device which stores the electrical energy in the form of electric field. Now how electric field will be there? For electric field we need charge, so charge is also required. So that means it is basically storing the charge, keeping the charge, and that charge gives the electric field, and in return we are getting the electrical energy. Now this is the basic definition of capacitor. Now it is also arrangement of conductors. You can say that it is also arrangement of conductors in which electrical energy is stored. So if I take two conductors of any shape, suppose this and this, and one is given positive charge and the other is given negative charge. Naturally, by the rule of electrostatics, the positive charge will accumulate towards this surface and the negative charge will accumulate towards this surface. So electric field are generated, electric field setup. What we can observe that due to electric field there is a potential difference that also set up between the two. In this arrangement you see that in this region between the two conductors the electrical energy is stored, and this electrical energy is why due to the charge. So this is also a capacitor. It is not essential that you have to give charge to the capacitor. Even though if you are not giving charge to the capacitor, then also the arrangement of two conductors behaves as a capacitor. Why? Capacitor is basically like a bucket full of water, and if the bucket is filled with water, then also it is bucket, and if the bucket is not filled with water, then also it is bucket. In the same way, the water basically is like the charge. So charge is kept, charge gets its place in the capacitor. Now what I would like to tell you, that in the capacitor, and you might have observed that battery also stores energy, electrical energy, and capacitor also stores energy. What is the difference between the two? In battery the energy is given out at a determined constant rate, whereas the capacitor gives the total energy at a time. For example, in your old camera you might have observed that there is a flashlight. Now when you switch on the flash, or when the flash is working, that much amount of light is not possible with the 1.5 volt or 3 volt battery. Then there is basically a capacitor which stores the electrical energy, and all energy is given at a time, which behaves as a, which gives you the large amount of light. So if the total energy is given out at a time, it is the function of capacitor, whereas if slowly you are draining the energy from the source, then it behaves as a battery. So in capacitor there is a potential difference, so conductors are there. Now here you see that some electric lines of force are wasted. Some electric lines of force are wasted. So what I mean to say here, for a better arrangement of capacitor, I am giving you two arrangements. One arrangement A, arrangement of two conductors, I am giving you in this way. Suppose there is one arrangement of conductor and another arrangement of conductor is in this way. Same conductor is there. It is given charge plus Q, it is given charge minus Q. It is given charge plus Q, it is given charge minus Q. So it will reside in this way. Now which one is better arrangement for capacitor? In capacitor you will observe that here the loss of electric lines of force is minimum. You see, there is minimum loss of electric lines of force, whereas here it will go in this way, it will come here, here it will go. So this arrangement is better arrangement. This arrangement is better arrangement, that in this arrangement you will observe that maximum lines of force are being between the two conductors. So this space contains the volume between the two conductors contains the electric lines of force, so the electrical energy is stored in it. And this is some loss is there. So loss should be, and in this course of discussion, what is important to understand, what will be the best possible arrangement of conductors so that we can obtain the capacitor. Naturally, the natural selection will be your parallel plates. You see, the parallel plates are there. In parallel plates, you will observe that the loss of electric lines of force is minimum. So this is the best arrangement, and therefore we study the parallel plate capacitors. It is the parallel plate arrangement that is the most popular, and it is convenient also, easily to construct, easily it can be constructed. So this is the thing that you all should keep in mind about the parallel plate capacitor. Now if the plate separation is D, if the plate separation is D, here is the electric field that is generated, and the potential difference delta V is there. So this delta V is basically E into D. Potential difference is electric field into distance. This delta V is there. Now what I would like to tell you, this delta V has a upper limit, and for any combination of capacitor you are not supposed to exceed that upper limit of the arrangement. If you will exceed that upper limit, then the properties of the plate will change and it will be destroyed. So this delta V has a upper limit for every arrangement, and you are not supposed to cross that upper limit. This is the first point. And what is this delta V? Delta V is potential difference. This potential difference delta V is basically V plus minus V minus. What does it mean? This is potential due to positive plate, electric potential due to positive plate, and this is electric potential due to negative plate. So this is your potential difference. And now you have understood that in this discussion, here one thing I would like to tell you, that it is not essential that equal charge needs to be given. It is not essential that, but the opposite face of the parallel plates, equal charge and opposite charge will automatically develop. See how? For example, now for example, I would like to tell you that suppose there are two plates. Here 3q charge is there, here minus 2q charge is there. Then also you will observe the extra charge that is given according to the rule of electrostatics. Extra charge is how much? 3q minus 2q, that is your q. Out of this q, here on this surface will be plus q by 2 and here on this surface will be minus q by 2. This plus q by 2. This is on the additional side. Now you see, in this surface if you will find the charge, it will be 3q minus q by 2, that is 5q by 2. And if you will observe here the charge on this surface, you will get minus 2q minus q by 2, that is minus 5q by 2. So it is not essential that equal and opposite charge should be given, whatever amount of charge you will give, but on this side you will observe that there is always equal and opposite charge. On this side you will observe that there is always equal and opposite charge. This is your thing that you should understand properly. Now, after this, if I want to tell you about if any conductor is there, it is found that whenever you give charge to the conductor, its potential raises. So Q is proportional to V. The potential in the arrangement of two conductors, the Q is proportional to V. V is what? Potential difference, and Q is the charge given to the conductor. After that, we need a sign of proportionality, that is Q is equals to CV. Here C is a constant. Right now I am not giving name to it. Later on we will decide what name should be given to this value C. Suppose a case, if an arrangement is there in which very small amount of Q you have given and very large amount of potential difference has been created. Under this situation, the value of C is very small. For a small value of Q, very large potential difference has been created. So this value has got very small value, and that arrangement is not useful for making the capacitor. That arrangement is useless. That arrangement has no use at all. Now second case, if the value of Q is very large and the value of V, potential difference, is very small, then this C has very large value, and that arrangement is suitable for making the capacitance. So C has got the name capacitance. Capacitance. C is the capacitance, it is the quality. Now when C is the capacitance, unit should be Q by V, that is Coulomb per volt, and this is called your Farad. This is called your Farad. So unit is Farad. Also it is a scalar quantity. It is a scalar quantity. Here you should understand very carefully that C depends upon shape, size and placing of conductors. Generally the student understands in this way that if Q is increased, so therefore C is equals to Q by V. If I will ask the question, if Q is increased, you will say C will increase, but that is not the case. If V will increase, then C will decrease. That is not the case. There is no inverse and direct. This ratio is constant. If Q is increased, V also increases in same proportion. So C does not depend upon Q, C does not depend upon V. It depends upon shape and size of conductor. So C does not depend upon Q and V. C does not depend upon Q and V. This thing should be understood in a very proper manner, because generally the student has a confusion that if Q is equals to CB, if V is increased, C will decrease. This is the general answer, but it is not correct. C does not depend upon Q and V. In the same manner, you can say that if a bucket is there, bucket does not depend upon the capacity of bucket, does not depend upon the amount of water that you give, or the level, what the water level is there in the bucket, on that the capacitance of bucket does not depend. In the same manner, capacitance of a capacitor does not depend Q. Q corresponds to water and V corresponds to level of water. So this is potential difference and this is charge. So C does not depend upon Q and it does not depend upon V. This thing should be clearly understood in your mind. Now how to find capacitance of a capacitor? Question arises that how we are able to find the capacitance of a capacitor. So there are few steps that we have to follow. For finding the capacitor, few steps are there. What are those steps? First step, give charge Q, plus Q and minus Q, plus Q and minus Q. First step is this. Second step is find electric field. Now electric field, when you are finding the electric field, two situations are possible. One situation is that electric field is constant and another situation is that electric field is variable. After finding electric field, what we have to do? We have to find the third step, potential difference. Potential difference delta V. And this delta V you will be finding, you will be using two methods. You will be using E into D for what? For constant electric field. When electric field is constant, and you will be using E into dr integration when electric field is variable. So you will be getting potential difference. And the fourth step that you will be taking, C is equals to Q by delta V. In this way we will be finding the capacitance. So these are the four steps that we have to use in order to find the capacitance. The four steps that we have mentioned, how we can apply those four steps in finding the capacitance of a capacitor, that we are seeing by an example. Suppose an example is there in this way. One example is given in this way, that the parallel plates are given with plate area A, surface area of plates, D, separation between the plates, and air is filled between them. Here is the D, and you have to find the capacitance of this arrangement. Find capacitance of this arrangement. Find the capacitance of this arrangement. Now what we will do? First step, we have to give charge. So plus Q minus Q. First step. Second step, we have to find the electric field. Now see, due to positive charge, the electric field will have this direction, and here the negative charge, the electric field have this direction. So this is electric field due to positive charge. This is electric field due to negative charge on the plates. So what we have seen in the Gauss theorem, that E due to positive plate, due to conductor plate, is your sigma by 2 epsilon naught. What is sigma? Sigma is surface charge density, Q by A. E due to negative plate, sigma by 2 epsilon naught. Sigma by 2 epsilon naught. So net electric field between the conductors, E net is equals to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is sigma by epsilon naught, that is Q by A epsilon naught. Epsilon naught is the permittivity. Now second step we have completed. Now what is the third step? Third step is to find the potential difference, and here you see the electric field is constant. When the electric field is constant, potential difference delta V is equals to E net into D, that is Q by A epsilon naught into D. And fourth step, we have to find the capacitance. So capacitance C is equals to Q by delta V is equals to epsilon naught A by D. So what result we are getting? C is equals to epsilon naught A by D. This is the value you are supposed to understand, and then you will be able in finding the capacitance of this parallel plate arrangement, which is basically your parallel plate capacitor. Now we have to understand the capacitance of a spherical capacitor. Capacitor is basically the arrangement of two conductors. So a spherical capacitor will be the arrangement of two spherical conductors. So our next discussion is spherical capacitor. You have understood that two arrangement of two conductors should be there. I am taking one spherical conductor, other spherical conductor. Center is here. This is A, this is B. And here I am giving plus Q charge, here it is minus Q. First step, I am trying to find the capacitance. Now in this situation, how first step I have given the charge. Now the problem is to find the electric field. So this is the electric field. Here you see, here the electric field is variable. Why? Here you see the distance between electric lines of force is increasing. Here the separation is less, more, like this. So electric field is variable. So in order to find electric field, I am considering here a Gaussian surface. This is the Gaussian surface. I am considering here a Gaussian surface of radius r. So Gauss law says E into A is equals to Q in by epsilon naught. This is the Gauss law. Here I am writing this radius is r. Here is the area that I am considering. So E into A of the Gaussian surface, this is your Gaussian surface. So here area is 4 pi r square. Q in is Q by epsilon naught. Therefore E is equals to Q by 4 pi epsilon naught r square. This is the value of electric field we have got. As I told you that the electric field is variable, here also it is variable because r is variable. Minimum value of r is A and maximum value is B. So A to B the r is changing. So next step is what? Next step is to find the potential difference. So here potential difference delta V is equals to E dot dr. I am taking the magnitude and dr value r changes from A to B. This is giving you Q by 4 pi epsilon naught 1 by r square dr A to B, and this is giving you Q by 4 pi epsilon naught minus 1 by r A to B, and this is giving you Q by 4 pi epsilon naught 1 by A minus 1 by B. So therefore delta V is equals to Q by 4 pi epsilon naught B minus A by AB. This is the value we have got for potential difference. Now what is our last step? We have given the charge, we have found the electric field, then we have found the potential difference, and what is the last step? last step is to find the capacitance. Therefore, capacitance C is equals to Q by delta V, that is 4 pi epsilon naught AB by B minus A. This is the expression for capacitance of a spherical capacitor. This is the expression for the capacitance of a spherical capacitor. After this, I would like to discuss with you two special cases of this formula. What are those two special cases? Try to understand. First case that I would like to discuss, when there is a single spherical conductor, that means this conductor can be supposed to at infinity. And second case, when the separation between the two conductors is very small, when it will behave like a parallel plate capacitor. So let us try to understand these two cases. Now we want to discuss the case 1. Case 1. For a single sphere. For a single sphere, we can consider the second sphere to be at infinity. So, first sphere A is equals to R, radius of the sphere, and B is equals to infinity. Single sphere. We will put the value in this equation and we will get the result. So, C is equals to 4 pi epsilon naught AB by B, I am taking common 1 minus A by B. B will cancel. Now put the value of B to be infinity, that is A equals to R, so that is 4 pi epsilon naught R. This is the capacitance of a spherical conductor, single sphere. Now it is important to understand that the capacitance depends only upon one factor, that is the radius. Capacitance depends upon only one factor, that is the radius of the spherical conductor. Now take the case of case 2. When the separation between the spheres is very small, that is A is approximately equal to B and B minus A is equals to D. Very small. Separation is very small. In this situation, C is equals to 4 pi epsilon naught AB by B minus A. What I am doing? I am replacing it by A. So this is giving you 4 pi epsilon naught A square by B minus A is D. Now this quantity 4 pi epsilon naught A square, 4 pi A square is what? 4 pi A square is radius, area. A is radius, so it is area of a sphere. So it is your epsilon naught A by D. Now, for parallel plate capacitor also we have seen the same result. So a very important result is coming for very small separation of spheres, the spherical capacitor behaves as parallel plate capacitor. So for very small separation, that means if the separation between the two spheres is very small, then we can treat the spherical capacitor as the parallel plate capacitor. And we have seen, and this A is what? This A is the surface area of the sphere, and as the difference in radius is very small, so the area will be nearly equal of the inner surface and the outer surface. So in this way we have understood the parallel plate capacitor, the spherical capacitor, the concept of capacitor, and the other related problems, other related situations. And I hope that there will be a better understanding of you people in the discussion of this mode of discussion of capacitors. In next video I will be discussing few more things about this only. Bye. Goodbye to all of you.